VLSos here. This is a video lesson on solving an inequality. We'll work a couple of examples. Negative 5x plus 4 is less than 19. We're going to use the process of getting x by itself, alone and positive on one side. This is not an equation, it's an inequality, because the comparison symbol is one of the four inequality symbols, in this case less than. We should expect that there are many values of x, in fact an infinite number of solutions for x that make this inequality true. So when we solve for x, we're finding the boundary, and we'll take a look at the graph. That's what that means at the end. I'm going to proceed by undoing what I see by doing the inverse to both sides. I'm going to undo plus 4 by subtracting 4 from both sides. When I do, these cancel, leaving negative 5x. On the right side, 19 minus 4 is 15. And the comparison symbol in between is the same, less than. Negative 5x is less than 15. In this next step, I'm going to divide by negative 5 to undo multiplying by negative 5. When I do, the negative 5's will cancel out, leaving x by itself. On the other side, 15 divided by negative 5 is negative 3. The symbol in between is not the same. I have to switch direction. The reason why I switch direction is because I divided by a negative number. I divided by negative 5. Which is also the same thing as multiplying by negative 1/5. And I must remember that when solving inequalities, there's one extra thought to include in the algebraic process, and that is when multiplying or dividing, but we're thinking of division as multiplying by a reciprocal. In this case, of course, I divided by negative 5, but I can also think of it as multiplying by a negative number, negative 1/5. When multiplying by a negative, then remember to switch direction of the sign. In this case, the comparison symbol. I have x is greater than negative 3 as a solution to this inequality. That means that any value for x, and there are an infinite number of them, as long as it's greater than negative 3, then it will be a solution and make this inequality true. I can graph the set of solutions on a number line, one axis, because we have one variable. If we place negative 3 on the number line and 0 as a reference point, then the value negative 3 is not a solution because x has to be strictly greater than negative 3. So I put an open dot at negative 3 as a placeholder so that I can shade or show everything above it. Any value in the shaded region of the line is a value of x that works as a solution. Let's do a problem that is a little more sophisticated. 4 times the magnitude or absolute value of x plus 1 minus 2 is greater than 6. So we have an inequality, but we're also working with absolute value grouping symbols in the middle of the math. I'm going to proceed to solve this with the algebraic process. I'm going to first clear the minus 2 by adding 2 to both sides. When I do, 6 plus 2 is 8. These cancel out, leaving a 4 times the absolute value of x plus 1. And the comparison symbol in between remains greater than, because I only switch if I multiply or divide by a negative number. Proceeding, this 4 is not inside the grouping symbols. The absolute value bars act like parentheses, they're grouping symbols. And this 4 being outside means I can divide by 4, and the absolute value of x plus 1 remains. 8 divided by 4 is 2. The symbol in between is still greater than. It didn't switch because I'm dividing by a positive. Now I'm going to take the step to undo the absolute value bars. From a previous lesson, we know that the inverse of making a positive or negative into positive means that we're going to make a positive into both the plus and negative version. So I'm going to put a plus minus sign out in front to remind us that the plus and minus done to both sides cancels out the absolute value bars, and on the other side I've got both the plus and minus version of 2. But there's a little problem or something to remember with an inequality. In an inequality, making it positive 2 is not problematic, but making it also negative means that I have a second solution of negative 2, which, because of the nature of inequalities, changed the sign or the direction of that sign. So I now have to account for the fact that I've created the two solutions, one positive and one negative, by writing the two solutions as inequalities here, one of which is positive and didn't change the direction of the sign, and one of which is negative, which changed the direction of the inequality sign. So now I'm working with two inequalities combined as one solution process, and the final step in both is to subtract 1 from both sides. When I do, in the first one, 2 minus 1 is 1, and the symbol in between remains greater than. In the second one, negative 2 minus 1 is negative 3, leaving x by itself, and the sign in between was already changed but remains less than. And here I have the solution. There's multiple solutions, but it's a set of all x as long as x is greater than 1 or less than negative 3. On a number line, that would look like this. Make tick marks at the locations of the boundaries, so at 1 and negative 3. I need an open dot at 1 because I can't be equal to negative 1. I have to have an open dot there as a placeholder and shade everything above to represent greater than 1. And at negative 3, I also have an open dot because I can't be equal to negative 3 and only be less. So there's a placeholder and I shade below negative 3 in that direction. Any value of x that is within the shaded portion of the line, even though there are two regions and two boundaries, is a solution to the original equation or inequality.